Okay, let's unpack this. Picture a crowded, noisy table. Maybe you're at a loud gathering or, I don't know, a dimly lit dive bar.
Oh, yeah, we've all been there.
Right. And someone hands you a quarter. You have exactly one shot to bounce it perfectly off the table and into this tiny glass.
No pressure at all.
Yeah, zero pressure.
Yeah.
And, I mean, most people in this situation, they just grip the coin, flick their wrist, and basically pray to the gods of chance.
Totally. We usually treat this like it's a coin toss, like it's just pure luck.
Exactly. You flip it, and whatever happens, happens. But today, we are going to show you why luck actually has absolutely nothing to do with it.
Not a single thing.
We're taking a deep dive into transforming a seemingly random parlor trick into an exact, highly controllable science.
And the materials we are pulling from today make just a phenomenal case for this. We are looking at a detailed video breakdown alongside this remarkably rigorous sports science field guide.
Yeah, the one titled Quarter Bounce Biomechanics, which is just a wild title, by the way.
It really is. But the overarching theme of both these sources is taking back control. When you actually understand the underlying physics, how trajectories, momentum, and surface friction interact, you stop hoping for a good bounce.
Right.
You start engineering one.
And that transition from just hoping to actively engineering, that's what really hooked me here. The sources frame this as this deep study in applied physics and environmental adaptation.
Yeah.
But going through the materials, I realized my entire mental model was just completely wrong.
How so?
Well, before we even get to the throwing part, the guide spends pages just talking about the table. It seems like most people fail before the coin even leaves their hand just because they ignore their environment.
Oh, absolutely. The environment dictates everything that follows. The field guide categorizes this preparation phase as establishing the launch pad.
The launch pad. I love that.
Right. And to start, the equipment is highly specific. You need a standard quarter, not a lighter dime, not a heavier half dollar.
Why specifically a quarter, though?
Because its standardized mass provides this very predictable baseline for kinetic energy. You need that consistency. And then you also need a heavy-bottomed glass.
Okay, so no cheap plastic cups.
Exactly. Because when a coin traveling at high speeds strikes a target, that kinetic energy transfers. A flimsy plastic cup will just, tip over or slide right away from the impact.
Makes sense. So we have the heavy glass and the standard quarter. But the surface of the table itself seems to be the biggest variable here.
Huge variable.
Yeah, because the guide has this massive warning against bouncing on glass tables. And I initially thought, oh, that's just to avoid scratching the furniture. But the physics explanation went way, way deeper.
Oh, yeah. Glass tables are the absolute enemy of a controlled trajectory.
Really?
Yeah, it basically comes down to energy dissipation. When you bounce a quarter off a dense, hard surface like solid wood or granite, the surface refuses to yield.
Right, it pushes back.
Exactly. It forces the kinetic energy of your throw to rebound upward, pushing the coin into the air. But glass, however, is amorphous.
Meaning it's kind of flexible on a microscopic level.
Pretty much. When the quarter hits, the glass absorbs and spreads that energy out, almost like ripples in a pond. It just kills the momentum, leaving your quarter dead on the table.
Oh, wow. So it just totally eats the bounce.
Completely.
Okay, so assuming we find our perfect dense wood or granite table, we still have to deal with our own bodies. The biomechanics guide introduces this concept called the wrist lock.
Yes, a very crucial concept.
And I'm just trying to visualize how that actually functions in practice.
Well, think about the human arm as a complex system of levers and hinges. You have your shoulder, your elbow, your wrist, and, all your finger joints.
Lots of moving parts.
Right. And every time one of those hinges moves during a throw, it introduces a new variable. It creates room for human error.
So more hinges equals more chaos.
Basically, yeah. The wrist lock is a method of physical subtraction. Once you establish your grip on the coin, you freeze the muscles in your forearm to immobilize the wrist completely.
Wait, so you are basically turning your forearm and hand into like one solid, unbroken piece of bone.
That's exactly it. You shift the fulcrum of the movement entirely to your elbow and shoulder.
Oh, I see.
By removing the wrist hinge, the power comes from a much larger, more stable muscle group. You are isolating the movement to guarantee that the force applied to the coin is completely linear and predictable.
I mean, I can see how locking down the variables in your arm makes total sense.
Yeah.
But here is where the guide completely threw me.
Oh, what part?
I'm really hung up on this diagram they call the targeting reticle. It says in bold letters that you must actively ignore the glass.
Ah, yes, the golden rule.
But if I'm not looking at my target, How on earth am I supposed to hit it? It feels completely counterintuitive. It's like trying to throw a dart while staring at the floor.
What's fascinating here is how the human brain processes visual goals. When you lock your eyes on a target like a glass, your brain intuitively tries to calculate a direct, straight-line path to get there.
Which makes sense for a dart, but
But a bouncing coin does not travel in a straight line. It travels in a segmented arc.
Mm.
You have a downward line to the table, and then a parabolic curve up and into the glass.
oh, right.
So the glass is almost this optical illusion. It traps your focus on the end of the journey rather than the critical moment of impact.
That actually explains so much. The diagram shows the person's line of sight directed at a specific sweet spot on the table, usually just a few inches in front of the rim.
Exactly.
And the glass is literally labeled as a collision hazard in the guide.
Think of it like playing billiards. When you are trying to sink a ball, you do not aim your cue stick at the pocket.
Right, you aim at the cue ball.
You aim the stick at a highly specific point on the cue ball, knowing that the resulting geometry will send the object ball into the pocket. You are mapping the collision.
So you map the table collision, not the glass.
Precisely. If you hit that sweet spot on the table with the correct velocity, the physics just take over. The glass simply becomes the inevitable destination for the coin's natural trajectory.
Wow. You are managing the bounce point, not the end point. Okay, that actually clicks for me.
It's a huge paradigm shift.
It really is. So now that we know we need to stare at a spot on the table,
Yeah.
I need to know how to actually execute the throw. Because the sources are super adamant that there is no one-size-fits-all toss.
Definitely not.
If I'm sitting at that ideal hard granite table we talked about, what is the most reliable way to hold and release this thing?
So the field guide lays out a matrix of 4 distinct techniques, and each one responds to different environmental pressures. For a standard, hard surface where accuracy is your primary goal, you use the foundation of all throws, the classic pinch.
The classic pinch. Okay, how does that work?
You hold the quarter completely flat and horizontal between the pads of your thumb and index finger.
Just flat like a pancake.
Yep. And with that locked wrist we established earlier, you push downward and slightly forward.
Yeah.
Then you release the coin flat just before your hand touches the table.
Why flat, though? When I imagine tossing a coin, my first instinct is to flick it so it spins in the air.
Well, simply put, spin is chaos.
Chaos.
Yeah. When a coin spins, its ridged edges interact with the air resistance, which creates complex aerodynamic drag. But more importantly, when a spinning coin strikes the table, the angle of those ridges creates unpredictable friction.
Oh, so it might grip the table and just shoot off sideways.
Exactly. By striking the table with the coin perfectly flat, you remove almost all rotational energy. The flat face of the coin impacts evenly, resulting in a highly stable, completely predictable vertical bounce.
The geometry section of the guide describes this in incredible detail, too. It asks you to picture a 45-degree ramp.
Right?
It states that if you push down at a steeper angle, say 60 degrees, the coin pops up higher but travels less distance horizontally, meaning your required bounce point on the table moves much closer to the glass.
And conversely, if you push down at a shallower angle, like pushing forward more than downward, you rely heavily on horizontal momentum.
So that moves your necessary bounce point much closer to you, the thrower.
Exactly. You can micro-adjust your aiming point simply by visualizing different angles of descent.
That makes perfect sense for a hard surface where you get that clean kinetic rebound.
Yeah.
But what if you're stuck playing on a cheap plastic folding table?
Ah, the dreaded folding table.
Right, the kind that gives a little, when you lean on it. I've seen people try a hard downward bounce on those, and the coin just sinks into the plastic with a pathetic thud, like zero energy return.
Because soft surfaces absorb vertical energy, the plastic actually deforms microscopically upon impact, basically eating the momentum.
So what do you do?
When you recognize that environmental limitation, you have to pivot to the second technique, the frisbee flick.
Okay, the frisbee flick.
Your grip changes entirely for this one. You hold the back edge of the quarter rather than the flat sides between your thumb and middle finger.
The guide uses a skipping stone analogy here, which really helps me visualize it. You aren't trying to make one massive jump. You are trying to graze the surface.
Exactly. The physics of the shallow graze bypass the elasticity of the plastic table. Instead of driving the coin down into the energy-absorbing surface, you use a wrist flick.
Wait, a wrist flick, doesn't that break the wrist lock rule?
It does. You break the rule for this specific shot to toss the coin forward at a very shallow angle. The coin essentially hydroplanes across the solid surface. You convert your horizontal speed into a series of low, fast skips.
It's brilliant because it solves the soft table problem by avoiding that vertical impact altogether.
Exactly.
And I imagine that same horizontal skimming action makes it the perfect shot for covering really long distances across a massive table, too.
It really does. You are utilizing forward momentum to carry the object, letting those light grazing impacts barely interact with the friction of the table.
Okay, so we have the classic pinch for short-range accuracy and the frisbee flick for distance and soft tables.
Right.
But the guide shifts gears pretty drastically after that.
Yeah.
It moves away from precision and introduces techniques for, like, extreme scenarios.
Yeah, things get a bit intense.
For instance, sometimes these games are played against a clock, or multiple people are throwing at once and the first one to land it wins. The frisbee flick sounds elegant, but it takes time to travel. What do you do when you just need raw, frantic speed?
Speed requires a completely different biomechanical approach. This brings us to technique number 3, the flat slap.
The flat slap.
You place the quarter entirely flat on the surface of the table, then you press down hard on the top of the coin with your index finger.
So you're squishing it into the table.
Right. You build up immense downward pressure, and then you swiftly slide your finger backward, letting the coin snap out from under the tension.
The potential energy concept here is just wild. You're basically spring-loading your own finger against the friction of the table.
You are trapping the object. The moment that downward pressure is released, all of that built-up potential energy instantaneously converts into forward kinetic energy.
Wow.
The launch is so abrupt it occurs in a fraction of a second. It is unequivocally the fastest way to get the coin moving.
But I have to push back here for a second. The sources openly admit that accuracy is severely sacrificed with the flat slap.
True.
I mean, the friction of your finger releasing the coin is inherently unpredictable. So why would anyone willingly choose a high-difficulty technique that lowers their chances of a clean trajectory?
This raises an important question about strategy versus precision. In a high-pressure, speed-based environment, perfection is often the enemy of success.
Okay, how so?
Well, the flat slap allows you to launch 3 or 4 coins in the time it takes an opponent to carefully line up one classic pinch.
Oh, I see.
You are consciously trading mathematical certainty for overwhelming volume. You flood the zone, basically relying on the sheer number of attempts to compensate for the drop in individual accuracy.
You're sacrificing the math for the adrenaline. That's a fascinating strategic trade-off.
It really is.
Okay, here's where it gets really interesting for me.
Yeah.
What if speed isn't the issue, but the environment throws a massive roadblock at you? Let's say someone puts a tall pitcher of water right in front of your target glass.
Ah, the obstacle course.
Right, the skimming frisbee flick would just crash straight into the pitcher.
Obstacles require vertical clearance, which really demands the ultimate test of trajectory control. And this is the final technique in the matrix, the edge snap.
The edge snap.
It is specifically designed to bypass tall barriers or to drop a coin into an unusually deep glass.
The mechanics for this one took me a minute to wrap my head around. You pinch the quarter completely vertical, standing straight up between your thumb and middle finger.
Correct.
Then, you snap your middle finger down onto the top edge of the coin, driving it violently into the table.
To understand the physics here, think of a wedge club in golf. When a golfer strikes downward on the back of the golf ball, the steep angle of the club face pinches the ball against the turf.
Right, and it pops the ball high into the air.
Exactly. But more importantly, it imparts extreme backspin. The edge snap does the exact same thing. The friction of your finger dragging down the trailing edge of the vertical coin generates massive rotational force. The guide clocks this backspin at an astonishing 3,000 revolutions per minute.
3,000 RPM. I was trying to picture what that does to a small metal disc in midair. It's not just spinning, it's practically humming at that point.
Oh, absolutely. And that massive backspin functions as a gyroscopic stabilizer.
Right.
Think of a toy spinning top. When it is sitting still, gravity pulls it over instantly.
Right.
But when it is spinning rapidly, the laws of angular momentum fight gravity and air resistance, locking its orientation in three-dimensional space.
That's incredible.
The coin stays perfectly vertical in the air, creating a steep, high, arcing trajectory.
And because you drove the force straight down to pop it straight up,
Mhm.
the coin has almost zero forward momentum, right?
Yeah.
It's all vertical energy.
Precisely, which entirely changes your relationship with the environment. With the other shots, your bounce point is inches away from the glass.
Right.
With the edge snap, your bounce point must be positioned immediately at the base of the target. It peaks high above the obstacle, clears the rim, and falls like a stone straight down into the center of the glass.
Okay, so if you're listening to this, you now have a complete mechanical arsenal. You have the flat, classic pinch for precision, the grazing frisbee flick for distance and soft surfaces, the tension-loaded flat slap for volume and speed, and the gyroscopic edge snap for vertical obstacles.
It's a lot of tools in the toolbox.
It is. But honestly, reading all of this, I felt a little overwhelmed. Thinking about angular momentum and friction coefficients while standing at a noisy table. It just feels like a recipe for mental paralysis.
Oh, for sure. Information overload in high-pressure situations is a very real problem. And that is exactly why the field guide transitions from physics into psychology at the very end.
Right? The checklist.
Yeah, it takes all of this complex biomechanical data and synthesizes it into a mental model, a 5-phase execution checklist designed to reduce chaos.
It really reminded me of how a pilot prepares for takeoff. They don't sit in the cockpit trying to mentally calculate lift and drag equations. They just run through a methodical checklist to eliminate variables before the action even starts.
Exactly. It's a framework for decision-making. Phase 1 is purely observation. Assess the surface. Is the table hard or soft?
Okay.
Phase 2 is strategy. Select your trajectory. Are you optimizing for accuracy, distance, speed, or height? Because that dictates your technique.
Right, choosing from the 4 shots.
Phase 3 is physical subtraction. Establish your grip and lock your wrist to remove anatomical errors.
Lockdown.
Phase 4 is visual discipline. Calibrate your target by actively ignoring the glass and staring at the sweet spot on the table. And finally, Phase 5, execute.
It completely shifts your mindset. You aren't just reacting to the game. You are systematically diagnosing the physics of the room.
Very true.
But knowing that checklist intellectually isn't enough,
Right.
You have to wire it into your muscles. The source material outlines a very specific practice protocol, and it emphasizes starting incredibly small.
Because it is a process of calibrating your hand-eye coordination. The protocol dictates starting with the glass just 6 inches away, using the baseline classic pinch.
6 inches is barely any distance at all.
Yeah, but the critical insight here is that your goal is not to make the coin into the glass. Your sole focus is hitting your chosen sweet spot on the table repeatedly.
You're actively training your brain to trust the bounce point and sever its visual addiction to the final destination.
Exactly.
The guide is super strict about this too. Like, you cannot move on until you land 5 successful shots in a row at that short distance.
You build the neural pathways for a flat release and a locked wrist. Only when that consistency is absolute do you move the target back to 12 inches and introduce a new variable.
Like switching to the frisbee flick.
Right, to manage the longer energy transfer. It is a systematic escalation of physical variables.
So what does this all mean? We started this deep dive looking at a noisy, frantic activity played at crowded tables. An activity almost universally dismissed as pure random chance.
Just a parlor trick.
Right. But by unpacking these sports science guides and biomechanical breakdowns, we've uncovered a hidden matrix of potential energy, energy dissipation, gyroscopic stabilization, and anatomical discipline. You now possess the mental models to read the physical properties of a room, select the appropriate kinetic transfer, and engineer a predictable outcome.
If we connect this to the bigger picture, it reveals something profound about how we interact with the physical world.
How so?
So often, we attribute success or failure to luck simply because we don't understand the mechanisms at play. Taking a moment to analyze the why, why a soft surface kills momentum, why a locked joint improves linear force, why backspin stabilizes flight, that is the mechanism that turns chaos into a repeatable skill. You strip away the magic and replace it with mechanics.
You aren't hoping the universe gives you a good bounce. You are dictating terms to the physics of the table.
Exactly.
But I want to leave you with one final thought to mull over today. These sources meticulously map out the launch, the friction of the table impact, and the aerodynamic travel through the air.
Right, the flight path.
We have successfully conquered the space between your hand and the rim of the glass. But what happens the exact millisecond the quarter crosses the threshold and enters the glass?
Oh, wow.
Think about the fluid dynamics. Think about the cylindrical shape of the glassware and how it funnels acoustic shock waves. Think about how the surface tension of a liquid reacts when a metal disc spinning at 3,000 RPM slams into it.
That is a whole different ballgame.
It really is. Conquering the solid mechanics of the table is really only half the battle, mastering the chaotic fluid dynamics inside the glass. Well, that might just be your next great deep dive.